Welcome to the fourth episode of our trigonometry lessons in advanced level mathematics. I am Bright Wokwesiga Nelson Amot. In the last episodes, we have been able to look at introduction to trigonometry. We have handled ratios of common angles and the quadrant system, and we have been able to handle the addition formulae. Now in this episode, we are going to handle multiple angles and submultiple angles. From what we have already seen in the previous episode of addition formulae, we were able to discuss and use these three identities. The identity for sin A plus B, for cos A plus B, and for tan A plus B. Now what if B is equal to A? If B is equal to A, then we shall replace the B in each of these three identities with A. What was sin A plus B becomes sin A plus A, which is 2A. Then we would have sin A cos A, because now even B is A. Even here we shall have sin A cos A. So we'll have sin A cos A plus sin A cos A, we get 2 sin A cos A. The learner can pause the video and verify that we shall have results for cos 2A and for tan 2A if we replace the B in these two identities with an A. What we have as a special interest is cos 2A. Now, if you have the cos of 2A, we are replacing the B with an A, so that we have cos A minus sin A sin A. This will become cos squared A minus sin squared A. Now, this one becomes our first identity to use for the double angle 2A, that gives us cos squared A minus sin squared A. Now, what if we want to get this second part of the identity? We can replace sin squared A with sin squared A can be replaced with 1 minus cos squared A, because remember that sin squared A plus cos squared A is equal to 1. So if you make sin squared A subject, you get 1 minus cos squared A. This will reduce to, this becomes a plus, and we have 2 cos squared A minus 1, which is that one. Also, from this very step, we can choose to eliminate cos squared A, so that we get cos of 2A is equal to, now in the place of cos squared A, we can put 1 minus sin squared A, then minus this sin squared A. This will give us 1 minus 2 sin squared A. So depending on the circumstances, on what you want to apply, you can either use cos 2A as cos squared A minus sin squared A, or you use 2 cos squared A minus 1 for cos 2A, or you use 1 minus 2 sine squared A for the same. Okay. Now we can proceed to relate this one. We are trying to look at the multiple angles, especially double angles, 2A. Now we want to make it a general relationship so that it can apply across the board. Here we have seen that a 2A is becoming an A this side. A 2A is becoming an A this side. Remember that the A is half of what is on the left, which means if we bring in a general coefficient K, for example, if I say sine 4A, now sine 4A, now my K is 4. Whatever is on the left must be halved to give what is on the right. So this becomes Ka over 2. So it becomes 4A over 2, which is 2A. So it becomes 2 sine 4A over 2, which is 2A, then cos 4A over 2, which is also 2A. As you can see, the one on the left has been halved to give what we have on the right. If I have, for example, cos of 5A, I will just have to look for half of this angle. So what I can get, cos squared, half of 5 is 5 out of 2. It becomes 5 out of 2A minus sine squared 5 out of 2A. So the concept is getting half of what is on the left. If I have, of course, this also applies to the other ones when you are trying to bring it in terms of cos squared and sine squared only. Now, what if we have tan of, for example, theta? Now here is our K is 1. So using this expression, we're supposed to have half of theta. So now it will be half of 1 theta, which is theta over 2. So I will say 2 tan. I'm just applying this expression. Now this A was half of 2A. So half of theta is theta over 2 out of 1 minus tan squared theta out of 2. So we shall be applying it like that. Now here we are dealing with submultiple angles, from a big angle to a small angle. From a small angle to a big angle, we're looking at multiple angles. So we can express angles, trigonometric ratios of angles, in terms of the ratios of half of those very angles. That's what we are dealing with under multiple and submultiple angles. Let's go to the examples and we try to apply these concepts. Example 1 is saying, if tan theta is 4 out of 3, calculate the possible values of tan theta over 2. Tan theta is 4 out of 3. Now they want the possible values of tan theta over 2. Now, as we have seen before, this tan theta, hope you were able to pause and write down those excuse me, and write down those identities for the half angles. Now, I want to move from theta to theta over 2. Theta over 2 is half of theta. So we apply the identity for multiple angles, whereby tan theta becomes 2 tan theta over 2 out of 1 minus tan squared theta over 2, giving us 4 over 3. We can now cross multiply. We get 6 tan theta over 2 being equal to 4 into 1 minus tan squared theta over 2. Now, since we want tan theta over 2, we can rearrange this equation in a quadratic form. When we rearrange, we get 2 tan squared theta over 2 plus 3 tan theta over 2 minus 2 is equal to 0. Please kindly, you can pause this video and you try to open and rearrange this expression to arrive at what I have got here. Now, after reaching here, since we want to solve for tan theta over 2 as in the question, we are now going to let our tan theta over 2 to be m or any other known, so that we are able to easily work out what we need to get. Now, we have got that one. We put 2 m squared, because I'm replacing now tan theta over 2 with m, plus 3m minus 2 is equal to 0. Now we have got a degree 2 equation which is quadratic in nature, and solve for that m. You can use very many methods. You can use factor method, you can use the formula method, or any other that you feel is simple for you to use. Me, I'm going to use the factor method. Numbers, I multiply, I get negative 4, add, get 3. That is in negative 1 and positive 4. So 2m squared. I'm replacing this 3m with those two factors, minus m plus 4m minus 2 is equal to 0. We'll have an m into 2m minus 1, that is for these two, plus a 2 into 2m minus 1 for the last two. This one to give me 0, which means I will have m plus 2 into 2m minus 1 is equal to 0. They will have m is equal to negative 2, or I will have m is equal to a half by equating each of those two brackets to 0. But what was our m? Our m was tan theta over 2. So therefore, tan theta over 2 is equal to negative 2 or a half. Now we have found the values of tan theta out of 2. Next question. Show that tan 22.5 degrees is equal to root 2 minus 1. Show that tan 22.5 is equal to root 2 minus 1 without using tables. Or without, when they say without using tables, it means also you can't use calculators. Those are electronic tables. Now, we are going to look at this. Now, 22.5 is not among our common angles where we were using thirds, because it was 30, there was 60, there was 45, 0, and 90, and the corresponding angles in the other quadrants. They are the ones that we memorized in our second lesson about ratios of common angles. Now, for this one, 22.5 is not among the common angles, but it is half of 45. So since we know tan 45 as 1, then we can rely on that one to get tan 2.5. So we begin with what we know with the common angles. These ones which involve surds, they always come from those common angles. Always try to figure them out in terms of the common angles that they have mentioned. So tan 45 degrees is equal to 1. That one we know from the quotations of common angles. Now this tan 45 in terms of the half angles of 2.5 is the same as 2 tan 22.5 degrees out of 1 minus tan squared 22.5 degrees is equal to 1. Now, I want to get tan 22.5, so I must make it subject if possible. So 2 tan 22.5 is equal to 1 minus tan squared 22.5. I can now rearrange. I will get tan squared 22.5 degrees. So this one is crossing the equal signs. Plus, it finds there this one. 2 tan 22.5 degrees. This one goes as a negative minus 1 is equal to 0. Again, I'm having a quadratic. I can let k to be tan 22.5. So how to get k squared plus 2k minus 1 is equal to 0. Now we are going to solve for the value of k, which is our tan 22.5. Now, again, here you have a choice of either using factorization formula, anything that is applicable and simple for you. Now, numbers multiply, you get negative 1, you add, you get 2, are not there. So we can solve this using the formula method. K is equal to minus 2 plus or minus the square root of 2 squared minus 4 times 1 times negative 1. You can visit our YouTube page, and you try to look for a video on quadratic equations, so that if you have forgotten these concepts, you are able to revise them. So this positive 1 value of a. So I have negative 2 plus or minus square root of 8. This is 4 plus 4, 8 out of 2. Now 8 is 2 times 4. Now root 4 is 2. So 4 goes outside as 2, even with 2 root 2. So root 8 is the same as 2 root 2. 2 root 2 out of 2. The 2 goes with the 2, goes with the 2. You remain with negative 1 plus or minus root 2. So either tan 22.5 degrees is equal to negative 2, not negative 2, it is negative 1 plus root 2, or negative 1 minus root 2. Now our proof was requiring us to find it as root 2 minus 1, which is the first one. So therefore, tan 22.5 degrees is root 2 minus 1 as required of us. Question number 3 says, given that cos 30 is equal to root 3 over 2, show that sin 15 degrees is equal to 2 minus root 3, all of it under square root sign, divided by root 2. Again, once we see this, our mind should run very fast to the common angles, ratios of common angles. And these are 30, that is 60, 45, 0, 9. Now, we have 30 already here, mentioned cos 30 as root 3 over 2. Now, they want us to find the sine of 15. Now, 15 is half of 30. 15 is half of 30. So we shall use some multiple angles to work on this problem. So now, but again, here we have cos, there we have sine. So we have to look at the identity which relates the multiple angle 30 to the submultiple angle 15, but using only the sine ratio. So we shall be forced to use cos 30 is equal to 1 minus 2 sine squared 15, because 15 is half of 30. So we have root 3 over 2 is equal to 1 minus 2 sine 15 degrees. Remember, our aim is to make sine 15 subject. So this one can go to the right, the left, and this one can come to the left. So we'll have 2 sine squared 15 degrees is equal to 1 minus root 3 out of 2. 1 sine 15, so I can divide through by 2. So sine squared 15 degrees will be a half minus root 3 out of 4. Next, we are now going to find the LCM on the right. Sine squared 15 degrees now becomes LCM is 4. 4 divided by 2 is 2. 2 times 1 is 2. 2 minus root 3. Since I need sine 15, I can find the square root on both sides. So sine 15 degrees is equal to root of 2 minus root 3. Now root of 4 is 2, which is as it was required of us. We now proceed to question number 4. Question number 4 says show, it's a proof, it's good. Show that sine 2a out of 1 minus cos 2a is cot a. On the left, we have double angles. On the right, we have half of 2a, which is a. So which means we are going to express this sine 2a in terms of the singular angles, this cos 2 in terms of the singular angles, then we simplify. However, there is a catch here. Cos 2a is a cos a over sine a. So in the denominator, We have cos sin A this side. So also when you're trying to expand the cos of 2A out of our three available choices, we shall use the one of cos 2A is equal to 1 minus 2 sin squared A. So left hand side, sin 2A is 2 sin A cos A, then 1 minus, now cos 2A is 1 minus 2 sin squared A. Opening bracket, we shall get 2 sin A cos A. 1 take away 1 is 0. 1 take away this. Now, negative and a negative is a positive. So remain with 2 sin squared A. Now the square will go with the sign, the 2 will go with the 2, and you remain with cos A out of sin A, which is cot A. That gives us our right hand side. We now go to question number 5. Question number 5 says, show that sine of 16 cos theta sine of 16 theta over sine theta is equal to 16 cos theta, cos 2 theta, cos 4 theta, cos 8 theta. What I can realize here is that I have a 16 theta which has been decomposed into smaller angles, 8 theta, 4 theta, 2 theta. So to arrive there, I will begin with the only available way of breaking down sine 16 theta, which will be in terms of 2 sine cos. The angles involved will be half of 16. So left hand side, sine 16 theta is 2 sine of half of 16, which is 8 theta, then cos half of 16, which is 8 theta, out of sine theta. Already you are seeing that our thing is coming out. So this will be now 2 times. Now the 8 theta again can be decomposed further to give us half of 8 is 4. So it will be 2 sine 4 theta cos 4 theta. This one only applies for h2 for sine 8 theta, then cos of 8 theta. Again, this one can be decomposed further. So you'll have this is a 4. Then this one alone will be 2 sine of this half of this angle, 2 theta cos 2 theta, then cos 4 theta, then cos of 8 theta. Again, this sine 2 theta, we are forgetting our denominator. Down there is a sine theta, down there is a sine theta. Now we shall have, now this and this gives us 8. But again, this sine 2 theta can be decomposed to give us 2 sine theta cos theta. Then we still have our cos of 2 theta. We have our cos of 4 theta. We have our cos of 8 theta out of sine theta. Now this sine theta will go with this sine theta. Then we shall have 8 times 2 is 16. 16 cos theta, cos 2 theta, cos 4 theta, cos 8 theta as our required right hand side. We now go to question number 6. Question number 6 says show that 1 plus tan squared a over 1 plus tan a all of it squared should be able to give us 1 over 1 plus sine 2a. Now we are moving from the small angle a to the double angle 2a. But what I can see as we start this process, we can realize that the numerator straight away reduces to sec squared a. Then down we shall have 1 plus, now I'm opening this bracket, 1 plus 2 tan a plus tan squared a for the denominator. Again, these two will give us sec squared a. It will give us sec squared a plus 2 tan a. Next, we are going to see that up we have a 1. So to create a 1, either we shall divide through by sec squared a. So dividing by sec squared a, 1 over sec is cos. So if you divide by sec squared a, it is the same as multiplying everything by cos squared a. So we shall get sec squared a times cos squared a out of sec squared a times cos squared a plus, now 2 tan is the same as saying 2 sin a over cos a. We also multiplying that term by cos squared a. So multiplying by cos squared a on each and every term will cause no change. Now here we have a 1 up, down we also have a 1, then cos a will go with the power. Now 2 sin a cos a is sin 2a, which brings us to our right hand side as it was required to be proved. I got question number 7. Question number 7 says show that tan squared pi over 4 minus theta over 2 in brackets is 1 minus sin theta over 1 plus sin theta. Now, usually you see that one, pi over 4, you have to relate radians to degrees. So pi out of 4 is 45 degrees, and tan 45 degrees is 1. So in your mind, that one should be there at the back of your mind, that since I have 45 and this tangent is 1, then I can see where I'm actually going to end up. Already you are seeing signs of a 1 coming because of tan pi out of 4 or tan 45. So let's go. Now on the left hand side, what we have is the same as saying tan pi over 4 minus theta over 2, the whole of it squared. Now inside here we can apply our addition formula, and this will give us tan pi out of 4 minus tan theta over 2 out of 1 minus tan pi over 4 tan theta over 2, but the whole thing is squared. Now tan pi out of 4, trying to maintain some good blackboard management. Now tan pi over 4 is 1 minus, add tan 45 of course, tan 5 is 1 out of 2 out of 1 minus tan theta over 2, but the whole thing is squared. Down is, there is a plus somewhere, it is a plus in the denominator, sorry. Now we are going to expand these expressions. Shall get 1 minus 2 tan theta over 2 plus tan squared theta over 2. I will have 1 plus 2 tan theta over 2 plus tan squared theta over 2. 1 plus tan squared over 2 is sec squared. Theta over 2 is 2. And it is 2. Minus 2 tan theta over 2 over sec squared theta over 2 plus 2 tan theta over 2. Now we have this sec squared over 2 minus 2 tan theta over 2 out of that one. When you look at our expression, at our proof here, there is a 1 there. So how do I create the 1? I have to divide by whatever is in that place. So I have to divide through by sec squared theta over 2. And dividing by sec squared theta over 2 to bring a 1 is the same as multiplying this sec squared theta over 2 by cos squared theta over 2. So I'm going to multiply every term in this ratio by cos squared theta out of 2. So it will be sec squared theta over 2 times cos squared theta over 2. I'm going to turn this term into sine over cos. Now times cos squared theta over 2 out of sec squared theta over 2 times cos squared theta over 2 plus 2 sine theta over 2 out of cos theta over 2 times cos squared theta over 2. This gives us a 1 minus, this goes with the power 2 sine cos in terms of half angles gives us sine theta out of, this is 1 and that is sine theta. This has brought us to our right hand side as required of us. That was question number 7. Our last question is question number 8. It says if tan squared x is equal to 1 plus 2 tan squared y. If tan squared x is equal to 1 plus 2 tan squared y, show that cos 2x plus sin squared y is equal to 0. So we have tan squared x is equal to 1 plus 2 tan squared y. We want to make sure that this tan squared x translates into a double angle cos 2x, and the y has remained the singular angle. Now, here you have to make a mind plan how you're going to flow, reach the final answer before you start. Because with these things, it is easier for you to chop 2 pages and you come back to the left-hand side if you're not careful. So you must have a program that you're going to follow. Now, here, tan squared x, for me to reach cos 2x, I will have to bring in the sine squared. I bring in the cos squared in terms of x, so that I can be able to, if I get, for example, if I get cos squared x, I can relate cos squared x to cos 2x, because cos 2x is 2 cos squared x minus 1. That one can actually bring me to what I want. So let me begin with that straight away. I will have tan squared x. Let me first try this. Tan squared x is equal to 1 plus 2 tan squared y. Now I am thinking of another shorter way to arrive at my answer. How can I bring that? Because it to me looks to be a simpler method. If I think of tan squared x and thinking of how I can relate it to cos squared x, because it is what can bring me this. Now, the easiest way of relating tan squared x to cos squared x is by first bringing in sec squared x, which can come how? By adding a 1 on all sides. If I add a 1 here, 1 plus tan squared x, I add 1 on both sides, so it becomes 2 plus 2 tan squared y. So I will have this becomes sec squared x is equal to 2 into 1 plus tan squared y. So we will have sec squared x being equal to 2 sec squared y. This one can become now sec squared y. Now, to bring in my cos 2x, I have to first introduce cos squared x. So I will put a reciprocal on both sides for -1. So this becomes cos squared x. 1 over sec is cos. 1 over sec is also, but 1 over 2 is a half. Then 1 over sec is cos. Good. Now, I can now relate to what I want. Now, when you go back to when you go back to cos 2x, this is just from cos 2x is equal to 2 cos squared x minus 1. We can see from here, you can pause the video and make it subject. Cos squared x will be a half of cos 2x plus 1. So in the place of cos squared x, we can put, therefore, we can now say a half into cos 2x plus 1. I have now replaced the cos squared x is equal to a half cos squared y. Now this halves will go. I will have cos 2x plus 1. Again, cos squared y is the same as 1 minus sin squared y. So what you get, this one and this one will die. Then sin squared y comes this side. I will get cos 2x plus sin squared y is equal to 1, which is our, which is 0, because the other one has died, is equal to 0, which is our required proof. So we have been able to show it as required. That was multiple and submultiple angles. Watch out for our next video. In our next video, we shall still come back here and discuss more of multiple and submultiple angles, but this time we shall pick interest specifically in what we call the T formulae, or what we call tan substitution. So in our next video, we shall still be on the same topic, but this time we shall zero ourselves on the T formulae or the tan substitution, and we try to apply it in solving equations which involve trigonometric identities. Thank you so much.